Welcome to AI Peer Review. Today we're diving deep into an interesting paper. It's tackling a major speed bump, really, in how large language models, video LMs, handle long videos.
Yeah, this one's called QuickVideo, Real-Time Long Video Understanding with System Algorithm Co-Design. It's from researchers at University of Waterloo and CAI Lab, and, well, it's pretty relevant given how slow these things can be.
Absolutely. I mean, the core problem they're looking at is that processing long videos, anything more than just a few minutes, it's computationally heavy and slow, really slow.
It really boils down to two main things, right? First, just decoding the video itself, getting it from the compressed file into actual frames the AI can see.
Right.
And second, the pre-filling stage for the LLM. You end up with this just massive number of tokens representing the video.
Yeah, converting that raw video bit stream for like an hour-long video can take, what, almost a minute sometimes, just that first step.
Exactly. And then, like you said, each frame turns into hundreds of tokens, so you do the math.
It explodes. You get millions, potentially billions of tokens for long videos. And that just crushes current hardware, exceeds GPU memory, causes huge latency.
Yeah, the paper mentions Qwen 2.5 VL needing over 80 gigs of memory for an hour-long HD video. And that's running at only 2 frames per second, even with tweaks to the model.
Which is why the usual workaround is just sampling way less often, like 1 frame every minute or something.
But you lose so much doing that. All the fine-grained stuff, the motion, the temporal details,
Yeah,
it's gone.
exactly. That kind of sparse sampling really limits what the model can actually understand, especially for anything complex happening over time. So, okay, our mission today is to unpack how QuickVideo tackles this using what they call a system algorithm co-design.
Right, they've got 3 main innovations we need to break down, see how they boost the efficiency and, the practicality of it all.
So let's dig into those bottlenecks first. You mentioned sequential video decoding. Why is that such a big time sink, specifically for long videos?
Well, think about a standard video file. It's compressed, right? To feed it to the AI, you need the raw RGB frames. And typically, decoders just process the stream linearly, frame after frame after frame.
Okay.
For a short clip, maybe not a big deal. But for an hour of video, that's, tens of thousands of frames. Doing that one by one just adds up. It becomes a significant chunk of the total processing time, like we said, up to a minute.
It's funny, we optimize the heck out of the LLM architectures, but this basic decoding part sometimes gets overlooked.
It really does. It's this pre-processing step that just sits there eating up time, and then you hit the second wall, the pre-filling. The token volume we talked about, why is that pre-fill step so computationally expensive?
So pre-filling is where the model processes all those input tokens, the video tokens, any text prompt you give it, and calculates the initial attention states, the key and value caches for all its layers.
Yeah, with the KV cache.
Exactly. And the core mechanism of these transformers, self-attention, its cost, scales quadratically with the sequence length. So millions of tokens, the computation just goes through the roof.
And it's not just the compute, it's the memory too. Storing all those KV cache vectors for every token, every layer. That's the other killer.
That 80 GB example really drives it home. It's just a massive memory footprint. And it limits how long a video you can even try to process, or how many you can process at once.
You can think of that KV cache as the model's short-term memory, right? It's keeping track of what it's seen. Longer video, more stuff to remember, needs way more memory.
Perfectly put. And that's why just getting a bigger GPU doesn't magically solve everything. Which leads people back to that aggressive undersampling we mentioned.
Yeah, but it's such a compromise. You lose all the temporal dynamics, the subtle movements. If you're analyzing, I don't know, sports footage or complex assembly instructions, you need that detail.
Okay, so QuickVideo's answer is this system algorithm co-design. Let's break it down. First up, quick codec, the system level part, parallel CPU decoding. What's the idea?
So the core idea is simple but clever. Instead of one CPU core chugging through the whole video file sequentially.
The slow way.
The slow way, yeah. They split the video. They find specific frames called keyframes. These are frames that can be decoded on their own without needing information from previous frames.
Oh.
They use these keyframes to divide the video into smaller intervals, and then, crucially, they decode these intervals at the same time on different CPU cores.
So parallel processing for the decoding step, like opening more lanes on a highway. What kind of speed up are we talking?
They're showing like a 2x to 3x speedup compared to standard libraries, things like Daycord or Torch codec for hour-long videos. Figure 2 in the paper shows this pretty clearly.
And it scales better with more cores too, right?
Exactly. QuickCodec keeps getting faster as you add more CPU cores, even up to 64 cores in their tests. The other libraries kind of plateau much earlier, maybe around 16 cores, so that parallelization really pays off.
And that keyframe alignment is key because you can't just start decoding anywhere in a compressed video stream reliably.
Precisely. Most frames depend on others. Keyframes are the anchors. So QuickCodec finds these, splits the video into chunks that start and end on keyframes, ensuring each parallel process works correctly. Algorithm 2 outlines this.
And they only need one seek operation per core per interval.
Yeah, that's another efficiency game. Instead of potentially seeking around for every single frame you want, which some methods might do for sparse sampling, they seek once to the start of an interval and decode the whole thing. Much better for the denser sampling video LNs need.
Makes sense. Figure 3 shows it gets faster for longer videos too.
Right, for really short videos, maybe under a minute, the overhead of setting up the parallel stuff might mean it's not much faster. But once you get to 10 minutes, an hour, the advantage grows quite a bit. They mentioned like 1.7x faster for 10 mins, up to 2.1x for 60 mins compared to Chord.
They do note a limitation, though, in Appendix B and Figure 6. Something about very sparse sampling.
Yeah, so because QuickCodec decodes entire intervals between keyframes, if you're only planning to sample, say, one frame from a long interval, well, QuickCodec still decodes the whole interval.
So it does potentially unnecessary work in that very sparse case.
Exactly. In that specific scenario, a method that just seeks directly to the needed keyframes might be more efficient. They acknowledge this and suggest maybe future versions could be more adaptive, but for the typical use case they're targeting, reasonably dense sampling, it's a win.
Okay, got it. So that's QuickCodec speeding up decoding. Now the algorithm level part, Quick Prefill. This tackles the LLM prefilling memory and compute cost. What's the strategy here?
So Quick Prefill attacks that massive prefill cost we discussed. It uses two main tricks, group-based prefilling and KV cache pruning.
Let's start with a group-based strategy. How does that work?
Instead of trying to stuff the entire video's token sequence into the LLM prefill stage at once, which blows up the memory,
Right.
they divide that long sequence into smaller, separate groups, let's say G groups. Then they prefill each group one after the other, sequentially. The big benefit is that the peak activation memory needed during prefill drops by roughly a factor of G.
Okay, so breaking it into smaller chunks makes the peak memory demand manageable. Clever. What about the second part, the KV cache pruning?
So even within each group, generating the KV cache still takes memory. Quick Prefill adds a step during the prefill of each group. It tries to figure out which KV cache vectors are less important for the model's future calculations.
Less important. How do they judge that?
They calculate an importance score for the KV vectors. Equation 2 shows the general idea. They tested a few ways looking at key norms, value norms, attention scores. And they found that a simple one, called key norms, small, basically just the size, the L2 norm, of the key vectors works surprisingly well.
And based on that score.
They keep only a certain fraction of the most important vectors, aiming for a target retention ratio called RO. So if RO is a 0.5, they keep roughly half the KV cache vectors and discard the rest.
Effectively making the model selectively forget less critical information to save space.
Exactly. And the result is that the total KV cache memory needed gets cut down by about 1 divided by rho. So rho 0.5 means roughly half the KV cache memory.
Wow. How much does that hurt accuracy? Table 1 looks at this, right?
Yeah, Table 1 shows that with key norms, small, and rho 0.5, they kept over 95% of the original model performance on the benchmarks they used. So a big memory saving for a pretty small accuracy hit.
That's a really good trade-off.
Definitely. And their ablation studies in Figure 4 and Table 2 kind of confirm this. Changing the group size didn't impact accuracy much. Increasing rho, the retention ratio, brought accuracy back towards the baseline, as you'd expect. It's a nice set of knobs to tune smaller groups for less activation memory, lower rho for less KV attached memory.
Okay, so we have QuickCodec speeding up CPU decoding, Quick Prefill making GPU prefilling leaner. The final piece is how they stitch these together, the overlap execution scheme. What's the problem they're solving here?
It's the classic pipeline inefficiency, right? If you just run decoding, then run prefilling, your GPU is sitting there doing nothing while the CPU decodes. Then your CPU is mostly idle while the GPU crunches through the prefill. Lots of wasted time and resources.
So they want both working in parallel. How do they achieve that overlap?
They divide the video into even more smaller intervals where S is much bigger than the number of CPU cores sees. The CPU starts decoding, but it prioritizes the earlier intervals.
Okay.
As soon as the frames for the first group needed by quick prefill are decoded, the GPU immediately kicks off the prefill process for that group.
Ah, so the GPU doesn't wait for the whole video to be decoded.
Exactly. While the GPU is working on group 1, the CPU is already decoding frames for group 2, group 3, and so on. It becomes like a producer-consumer pipeline. CPU produces decoded frames, GPU consumes them for prefilling.
Figure 1 shows this visually, like a pipeline. The GPU only stops if it's waiting for the next batch of frames from the CPU, right?
Pretty much. They manage to get almost complete overlap, and the impact on total time is huge. Equation 3 describes the potential gain, and Figure 5 shows the actual result for a 30-minute video.
What was the speed up there?
They went from about 69.7 seconds end-to-end with a sequential baseline down to just 20.0 seconds with the full overlapped quick video system. That's basically a 3x speed up.
Wow, that's a massive difference for overall latency. They mentioned a tiny startup latency.
Yeah, just a small, unavoidable delay at the very beginning for parsing the video metadata, figuring out the keyframes and intervals. But after that initial setup, the pipeline runs very efficiently.
Okay, so let's pull this together. Key takeaways. QuickVideo delivers a really significant speed boost for long video processing and video LMs.
Yeah, by tackling both bottlenecks decoding on the CPU and pre-filling on the GPU simultaneously.
And it's this system algorithm co-design that's key. Quick codec for parallel decoding, quick prefill for efficient prefilling, and then that overlapped execution tying it all together.
It's a really neat example of looking at the whole system, not just optimizing one isolated part. And these techniques seem pretty general, working across different video lengths and sampling rates, at least within reason.
Plus, the reduced memory and compute needs make it more feasible to run these demanding models on, let's say, less extreme hardware.
Absolutely. This could really pave the way for video LMs that can handle longer videos, maybe at higher frame rates, leading to, much better temporal understanding.
QuickVideo definitely feels like a compelling step forward, making this kind of AI analysis on long videos feel much more practical, much more efficient. That combination of system tweaks and algorithmic tricks, plus the co-design for parallel work, it really hits the main pain points.
For sure. That 3x speed up on the 30-minute example while keeping accuracy high, that's a big deal. And the memory savings from the KV cache pruning address another critical barrier to just using these things more widely.
Yeah, this deep dive really underscores how important it is to look at the whole pipeline, doesn't it? From getting the data in all the way to the final inference. That's where the big real-world gains often are.
Totally agree. So for you listening, we definitely recommend checking out the paper itself if you want more details. The appendices have more on the interval logic and extra results. It also makes you think, right, what are the right trade-offs between speed and accuracy here?
That's the constant balancing act.
Yeah. And where does this go next? What other research will build on what QuickVideo has started? It's such a fast-moving field, and honestly, we're probably just scratching the surface of what's possible with understanding long-form video content.